All right, so my name is Javier Martí. I'm the founder and CEO of Divirod. Divirod is a Boulder-based company. We do water risks in a simplified manner. So the problem that we normally address is water risks. And water risk is something that people do appreciate every day. We look at water is so important that Databricks even provides water bottles, which is super good. And you think that we have enough knowledge about water, but we don't. Water, if it is contained in this particular jar, you think, okay, I know how much water is in here. But if I do this, I'm sorry, you don't know how much water is there, right? So you will see that the problems that we're facing as a society is the possibility of having floods, is the possibility of having droughts, and all the extremes in between. And how to characterize this in a way that we can actually adapt and become more resilient is what we do. Is we provide that solution and the data sets to provide the knowledge and the possibility to adapt and to evolve as a society. So when you're thinking about what is water data, that's something which is a combination of many things. So not only the direct measurements that we take from precipitation, soil moisture, water levels in reservoirs. On top of this roof, there's a lot of water when it's raining. Tidal changes, snow, you name it. Our mountains are full of water in many ways. But we also have other type of water data that are very relevant to the case and to the problem of addressing global water risks, which is everything related to weather patterns, population shifts, demand of water, and even the usage of water in agriculture, by all of us, by spilling on the floor, et cetera, et cetera. And nowadays, we're also counting with a very, very interesting mass of data, which is coming from social media. And everybody's taking photos of events. You've seen on the news, Lake Mead, that it's minimum, a village appears from the bottom. You look at Venice is sinking, Piazza San Marco is completely filled with water. It's a very interesting thing to see that not only we have direct measurements, but also indirect measurements about water. And we're trying to bring everything together in what I would call a global water platform. And as I was saying, the problem with water is that there is not enough data. Even though you can look at a map and you see a lot of dots everywhere, when you zoom in, the dots are becoming more and more dispersed. So if I'm asking you, do we have a water reading next to this building? The answer is no. It's going to be somewhere else. It's going to be in a harbor. It's going to be at a certain distance, some miles away from us, so we don't have a direct measurement of water in this particular place. So we suffer what we call water data scarcity. And the reasons why is because water is freaking difficult to measure. And you see that the guy in the stick on the mat is actually common practice. It's pathetic, but in the 21st century, we still put a stick on the mat, or we look at a ruler on a dam and things like that. So as a result, water is very disparate, water data. And it's full of antiquated technologies, and we're here to change that. So the context of our company as a whole is to look at the more frequent climate weather events. And those events are impacting us so badly that if we let them go, we're going to wipe out from the international GDP, we're going to wipe out about $6 trillion by 2050. And this is atrocious. We cannot stay still. We have to do something about it. And we need to bring up solutions which are at par with the problem. The problem is mega problem. And believe me, it affects us all sorts of industries. And to tackle this, our customers have been using predictions, have been using all sorts of modelings to look at how much will we have in 20 years. And the answer today is that, man, the weather is changing so much, there is no way that we have enough knowledge of what's going to happen in even 1 year. So who could guess that the Lake Tahoe was getting so much snow this winter? I couldn't, but was expected in a way. So the overall discussion here is that we need more data. We need more ground truth data. And it's very important that we come up with this digital ground truth. So one way of doing it is to aggregate everything that is possible, that is available in the market, everything that is publicly available, all this disparate, uncalibrated, manual or less manual data that is coming from publicly available sources. And we put them together into a single map. That's one thing. The next thing that you have to do with data is actually, who's a data scientist here? Who's not a data scientist could be faster? Okay, so everybody who's doing data science needs to know that, at least they know, you have to put all the data under a single format, a format that you can understand, reduce the gaps, take away the artifacts. I mean, get the cleaning of the data is the most painful thing because that's not data science, that's data cleaning. And bringing everything into a unified schema that actually allows you to do something meaningful with it. The next thing with water is actually, we're thinking about what is the zero, the vertical datum. That's a very strange concept, but if you think about where is the zero in the planet, like you can refer is 2 meters high or 1 foot low, what is that zero? And if you dig deeper and you investigate and you see all these concepts of MSL, MLL, W, all these wonderful things, space missions measuring the geoid and the gravitational effects so we understand what the zero is, it's a mess. It's actually quite a mess. We need to bring together water at the same, globally at the same vertical datum. And that's something which is quite difficult, but this is part of the problem. The other thing, of course, to combat water data scarcity is to augment the data sets. And we want to augment data sets with very quality-oriented data gathering mechanisms. And we see that, if you look at NOAA, for example, in Miami, what they have in Florida, a city which is actually exposed to a lot of flood risks, 3 gauges for them, that's not enough. I mean, the guy who's living, I don't know where the airport is, doesn't know how much the sea is going to impact it if it comes with in a big event. We have to move more towards the right situation. Left, right, yeah, right. So the right situation, which is get more data points on the map, get more sources of water data. And with that, we'll have a more geographically coverage altogether that allows to actually not extrapolate, but interpolate and understand what happens between the points. So we have to increase the density of collection. So with all this, you may think, what is the solution? It's a difficult one. So to work towards a solution, you have to think in terms of how data evolves as we treat it, as we progress in our marching from raw data and signals. How do we elevate all this to wisdom, to something that is really tangible and is useful and allows you to provide a very clear action to whoever needs to take the action? This is the challenge as a data company. This is a challenge that we're facing as individuals. Where do I get my information from? Think about when I live in Colorado, and I get these flash flood alerts very often. And it's like, okay, I'm getting them so often that the sky is falling, but never falls. So what about this? Do we need to have something which is real wisdom that can be integrated into action in a way that people trust? And I'm using things which are very philosophical: trust, actual wisdom, and knowledge. So the steps that we think we're taking as a company is actually very, can be summarized in 5 steps. The first one is to deploy the network and the infrastructure of our IoT solution. And our IoT solution is designed to be geographically dispersed, remotely located if it need be, and as dense as you want it. The second part of an IoT solution is to actually, the measurements that it takes, this little device, they need to be brought up to the cloud in a way that you brought it to the cloud when it's needed, not after the fact. And it needs to be very, you have to have a seamless connection if you really want to achieve real-time data. The third step would be processing the data at scale. So you need technologies like a Spark or similar that allows you to manage billions of data points at once. And that's not trivial, as you all know. And on top of that, you really need to have a continuous running of algorithms and artificial intelligence that is analyzing constantly the data that you have at hand. To make the whole thing complete, we go to number 5, which is make the data and information accessible. You can do it using Delta Lake. You can use it in different ways. My favorite one is actually to have it in their fingertips. And nowadays, everybody has at their fingertips something very common, which is a phone. So how cool would it be that this massive problem could be contained on a phone? In the same way you're calling an Uber, and it's going to pick me up at 2:05, and I know that. In the same way, you need to know if you're going to be impacted by a water event. And it's important to have that easy of access of information. Okay. So how do we handle this situation? So I talked about IoT devices, IoT systems. So our IoT solution is actually quite intriguing because it's about this size, can be put anywhere on the map in 15 minutes, even on top of the roof, and collects signals from a very large area, as you can see on the right hand of the picture. This solution is actually embedding a very sophisticated data collection mechanism that is transported to the cloud with the help of our partner, Deutsche Telekom, which allows us to bring the data to the cloud via cellular network or even satellite. We're one of the first companies to have delivered satellite IoT to telecom. And then, as I was illustrating over there, you see that we get the teeny tiny system on the tip of the iceberg kind of thing. And then we're collecting this reflection of water signals. And what are those reflections? This is pretty cool. If you think about all these satellites which are orbiting the ground, like GPS, we use them for what? We use them for navigation, right? But what is interesting is if you want to put together something like a passive radar system, you can use those signals, which are very precise, as transmitters of a radar. So when they hit the ground, they capture a signature, which is directly related to water. Bingo. All you have to do is just listen in passively to those echoes. So anytime we put an instrument out there, we're collecting about 20 echoes per second simultaneously. And this is amazing, like having a map of sensors in front of you, having a map of collecting individual units. That's the way that our technology works, and actually it provides us with all these many simple data types, which are not simple, but are actually quite useful. So we measure precipitation rate, we measure water levels, tidal changes, wave activity, soil moisture, snow, tides, ice, a lot of things with a very simple device, and transforming those signals in the cloud into the applicable data types. So what do we do with those signals when they come to the cloud? We actually process them through a pipeline. Very typical, very much. And we are using a process in which we're joining all the inputs that we're getting from every single collector and every single satellite. We compare it with all the tables which are telling us where the satellites are precisely located in a way that we can triangulate and we can know precisely where the reflection is coming from. We pass them into our models, and we make the conversions on the pipeline. So at the end of the day, we come in with very clear models of where the data is and how we tabulate all the data parameters that are relevant to water. A very important part of the process, and I'm going to put like a parenthesis here, is data quality. And data quality is important because as modelers, as data scientists, you know that you put the garbage in and then you get clean data out. No, you get garbage out. So with this dilemma, you really have to make sure that you address at least these four C's of quality: for completeness, congruency, continuity, and consistency. And what do they mean? Is that we need to have a good handle on all the data that is available so that we know we have a complete data set. We need to have congruent values which are actually relevant, are not artifacts. There's something that is actually within the expected range or behavior of what we're looking at. We need to have continuity. One of the things that we are actually quite proud of is that we have a continuity of 99.98% of uptime in our data delivery. That's sick. Man, think about it. Almost 100%. So we need to have that continuity in a way that we are not missing the event that led to a catastrophe. We're not missing the event which actually can inform an insurance company, things like that. And then the whole thing has to be consistent. So we don't want to have artifacts. I mean, how many glitches and blips are in the data sets are many, and we need to make sure that our data sets are actually clean as they can. So as I said before, I'm the CEO. I'm not a very technical person. This, if you see the program, there was 2 people here that should be on the stage. One is in New York and couldn't make it because of the flight, what is it, Eva? Apocalypse that we had this week. And then the other one couldn't make it either. So what I'm going to tell you is that the suite of technologies that we're putting together are integrating constant influx of data streams. We're putting together all of our, we have to store it, we have to condition it, we have to apply the quality metrics that I was mentioning before, and that's something that we do thanks to Spark Streaming. And then we place them and provide the access to the users via the different technologies that we all are very familiar with, especially in this conference. So I'm not going to be explaining what the Delta Lake is at the moment. So looking forward, what to expect in terms of water risks is the delivery. Well, how are we going to deliver these things? And what are the use cases that can actually help us all? So this is just to illustrate a solution, which is an early warning and monitoring solution. You have an asset at risk, one of these white houses. Is affected, is in a floodplain, like many other facilities, is impacted by water, like many other people in the world, but they don't know when. So they need to know with a certain amount of time, 6 to 10 hours, am I going to be impacted for real by a flood? And that's something that we can do with our data, and we can do with our analysis, and with all the technology stack that we put together. So these people are benefiting from different, depending on where they sit in the floodplain, they will benefit from more or less time to actually take an action. And typically, corporates that we work with, they put in place risk mitigation plans so that if a flood is coming, they deploy floodgates. They move the inventory from one place to another. They lift up the machinery. They remove the chemicals from the ground. And remove the chairs from the ground, the photo from grandma from the ground, everything up, up, up. And this sounds very little, like little actions. You would be impressed when you think about the millions of dollars that can be saved by just having that time. So thanks to this type of technologies, we are able to provide, avoid situations like the collapsing of a roof. I told you that we can put things on the roof. We do put things on the roof. We see a lot of dirt on the roof, a lot of water, and a lot of extra load on the roof, which is unnecessary. And we see situations like that actually, when they happen there, they're going to happen further down the watershed. And this is just to illustrate a flat propagation. We recently have provided our data sitting on the marketplace. And if you go into the marketplace, you can actually use this type of data. You can do things like this. You can look at the flat propagation. How much time is there? Sorry, I don't have a pointer, but let's take the, I'm looking like a air hostess. Do the first peak. The first peak is actually moving, is the first one that you will detect, is an immense amount of water raised in a given place. At the second location, you have the green curve, which is coming next. So you're seeing that this thing propagates. You can actually not model that. You can actually monitor that. Is be sure that you're actually seeing the trend. So you're sitting further down in one of the purple regions. You know that in a given amount of time, and this is kind of a very slow time propagation, but in a given amount of time, water is going to come to your place. So you can actually start analyzing and providing alerts about it. The other things that you can do with this type of data is actually make year-to-year comparisons. You have here two different cases, and I apologize, the graphs are very engineered. They're not very marketing-oriented. But you could see on the graph on the left, it's a repetition of the same sequence. You always have a same water cycle season after season after season. That's something I would call a safe situation, a very predictable situation. The situation, on the other hand, on the right-hand side, is what you're seeing these days. You're seeing that the green, the orange lines are actually not showing you that the water levels are kind of in the same arena, but they're kind of fluctuating a little bit. But then you have situations like this year or last year where you go through the peak of water excess, and that gives you a possibility to understand, okay, so if I was managing water and I have to deliver water to almond producers, to agricultures, to cities, I know how I managed the water when I was in the peak. But now if I change year, I can use that information and couple it to what you can do in a time of scarcity or in a time of excess of water. So a lot of things can be done using this type of data, and this is just a very small pics of what it is. This picture, anybody knows where it is? Venice, Venezia. So Venice is, and this in particular is a photo taken from Piazza San Marco into San Giorgio Maggiore, which is an island right across Venice, which unfortunately is sinking. The sinking, and at the same time, as you know, Acqua Alta, all the water, the tides are going up. And this basilica over there is one of the historical places in the world, is actually being affected. We're working with them. We're providing them with that, the ability to actually react to these situations. And they said, it's very sad that we were not informed on time, before we existed, because we lost racks, we lost documents, we lost books, we lost things which are never to be seen again. So if we want to preserve, we're going from water scarcity and consumption to protecting our own history. That's something that water data is essential. And I think with that, I'm going to leave you with data at your fingertips. That doesn't lead to my LinkedIn, but it's a surprise. So I invite you to take your phones. I know that everybody has a phone. And take a photo of that QR. And you can have your data from Venice at your fingertips. And thank you.